Today we're going to look at section 8.2, which is on graphing simple rational functions. An irrational function has the form f of x, where we're just going to have a function on the top, p of x, and a function on the bottom, q of x, where p of x and q of x are polynomials. And once again, q of x cannot equal 0. Because remember, we can never have 0 in our denominator. And any time that we have our denominator equal to 0, that is something that our domain cannot be. So it would be that value that would make the denominator equal to 0 is not in our domain. And when we talk about the parent function for a simple rational function, the graph of a parent function is f of x equals 1 over x. That's our parent function. And this graph is going to be called a hyperbola. And it consists of two symmetrical parts called branches. The domain and range are all non-zero real numbers. Any function of the form g of x equals a over x, again, a cannot be 0 because then it's just 0, has the same asymptotes, domain, and range as the function f of x equals 1 over x. So if we look at this, in the parent function, if we have this, it's going to be 1. 1 is one of the ordered pairs. This branch is going to go this way. This branch is going to go this way. We have -1, -1, and the branch is going to go this way. And we said the domain and the range are all non-zero real numbers. Well, essentially what that means is you're going to have a vertical asymptote at that dotted line of x equals 0, and you're going to have a horizontal asymptote at this dotted line y equals 0. So on both parts of these graphs, this will go infinitely closer and closer and closer to this line, but it will never touch it. It will get closer and closer to 0, and it will never touch it. And the same thing is going to be true on this side. It's going to get bigger and bigger and bigger and bigger and closer to x equals 0, but it will never touch it. And then the other branch is symmetrical, and it will be the same thing. So this point here is going to be 1, 1, and this point here, like we said, is going to be -1, -1. And that's what the parent function of this hyperbola looks like. So when we look at example 1, and we go to graph these, so in example 1, we are going to graph this rational function, and then we're going to compare it with the hyperbola of the parent function. So once again, if it is in this form, y equals 4 over x, we automatically know that we're going to have a horizontal asymptote at 0 and a vertical asymptote at 0. And so what I'm going to do is I'm going to plug in a couple of points. So if we put in 1, 4 divided by 1 is 4. We're going to have a point there. If I put in 2, and I'm only going to pick points that I see that are going to divide easily, because I don't want to get any decimals, fractions. It just is going to make life much easier to do this. So put in a 2, I'm going to get 2. Put in 4, I'm going to get 1. And that's enough so I can see what that pattern is going to happen on the right side, because I know it's not going to cross those asymptotes. So my graph on this side is going to look like that. Well, we know that on the other side, it's going to be symmetrical. So this branch of the hyperbola is going to be symmetrical. So if I put in -1, I get -4. If I put in -2, I get -2. And if I put in -4, I get -1. So here is the branch on that side. So now we've graphed the function. We want to compare it with the parent function. So here is our parent function. So we want to compare that graph with this graph. And so the way that we're going to do that is we're going to say the graph of y equals 4 over x lies farther from the from the axes than the graph of y equals 1 over x, which is, again, our parent function. We also know that both graphs lie in the first and the third quadrant, and they both have the same domain, they both have the same range, and they both have the same asymptotes. So if we look at this, our domain for this function would be all real numbers except for 0. So x cannot equal 0. The range for this function would be all real numbers except for 0. So y cannot equal 0 in this graph. So that is, if it's just in this form, y equals 4 over x, and we can compare it to the parent function. So the next thing we're going to look at is translating these. Now, the translations are going to be exactly the same as all of the other translations that we've done so far. H tells us how far are we moving right or left. And K tells us how far are we moving up or down. All right. So we're going to draw the asymptotes, x equals h and y equals k. Those are the two asymptotes for this graph. Plot the point to the left and to the right of the vertical asymptote. Draw the two branches of the hyperbola so that they pass through the points plotted and they approach the asymptotes. So it's going to be exactly the same thing as we did before, only now our asymptotes are going to be shifted one way or another, or up and down. So if we look at example 2, here, I know that here is our parent, or the standard form of our hyperbola, and this tells me that I'm going to shift my asymptote to the right 1 unit. And think about it this way. What makes that denominator equal to 0? If I go x minus 1 equals 0, I have to add 1 to both sides, and so I know that x equals 1. That's the number that will never be in the domain of this function because it would make our denominator 0. So we're going to have an asymptote at x equals 1. And then here, from our y, that tells us it's a vertical shift. It's going to shift the asymptote up 2 units. Well, it was at 0, 0. So here is our other asymptote. So those are the two asymptotes we're going to have. And now we just plug points in. So once again, I'm going to put in 2. So it's going to be negative 3. And if I put in 2, 2 minus 1 is 1 plus 2. So I have negative 3 plus 2, which is negative 1. And then let's plug in another point. Let's go with, well, it doesn't really matter, but let's go out a couple spots. So let's go 4. So it's going to be negative 3. 4 minus 1 is 3 plus 2. So that's going to be at 1. And so now I have 2 points. I kind of know what that's going to look like. So it's got to take both of those. There's that branch of my hyperbola. And now we're going to do the same thing with the other one. Now we're going to go to the left, and I put in 0. So if we put in 0, erase these. So if we put in 0, we're going to get negative 3 over negative 1 plus 2. So that's 3 plus 2, which is 5. And again, notice we should be in opposite parts of that graph. And these are going to be symmetrical. So let's come over to negative 2. So we're going to have negative 3 plus 2. So that's 1 plus 2, which is 3. And there's our graph of that one. So here's our graph. Now we have to state the domain and the range. And when we do this, you can do this a couple of different ways. Notice when the domain is our x values, we already said it cannot equal 1. So I could say all real numbers except 1. Or I can also say x cannot equal 0. Oh, sorry, 1. X cannot equal 1. So either one of those is fine, and our range is the same type of thing. All real numbers, except in this case it's 2, or you can say X cannot equal 2. So let's go ahead and look at one of these guided practice questions. They're all the same. So let's just do let's go number 3. That'll give us the vertical shift. So go ahead and do question number 3. Go ahead and pause the video, and then you can hit play when you are ready. So here is the solution to question number 3. Notice again, the domain is shifted to the right, or the graph is shifted to the right 3 units and up 2 units. So the domain is now x is not equal to 3, and the range y cannot be equal to 2. So realistically, we can tell us you could tell what the domain and the range is of these functions without even graphing them. For example, in question 1, it's in that standard form as a parent function, so we know the domain and range is going to be at x at 0 for the domain, x cannot equal 0, and the range is y cannot equal 0. For number 2, there's nothing in the denominator that shifts it one way or another, so the domain is going to be x cannot equal 0. And this one, number 2, the range is going to be y cannot equal -5 because it's shifted down 5 units. So remember, the number in the denominator is going to tell us where that domain restrictions are, and the number outside is going to tell us where the range restrictions lie. So the next thing we're going to talk about is other types of rational functions. So all rational functions of this form also have graphs that are hyperbolas. So if we see this, y equals, and then it's going to be some function in the numerator and some function in the denominator. So y equals ax plus b over cx plus d. The vertical asymptotes of the graph is the line x equals negative d over c. So essentially, we're solving for the denominator. Set the denominator equal to 0, find what the restrictions are. That's how you find the domain. That's the vertical asymptote. The horizontal asymptote is a over c. So if you have the same degree in the numerator and the denominator, it's basically just you're going to divide the leading coefficients. So the top leading coefficient divided by the bottom leading coefficient. So let's look at an example. So we're just going to do example 3. A. We'll do the first one. So graph the rational function of this form. So we have f of x equals x minus 1 over x plus 3. Well, this is a horizontal shift. So x plus 3 equals 0, so x equals -3. That is my vertical asymptote. I know that x can never equal -3. That would make my denominator 0, and my whole problem would blow up. The next thing, I see that these two are the same. The leading coefficient here is 1. The leading coefficient here is 1. And remember, it's y equals a over c. And a is the top one, c is the bottom one. So it's going to be a, which is 1, divided by c, which is 1. So that is going to be 1. So my horizontal asymptote is going to be right there. And then now you just plug in points once again. So what we're going to do is we're going to plug in a couple of points here. So go a couple to the right, couple to the left. So put in -4. If we put in -4, that's going to be -5 in the numerator. And -1 in the denominator. So that's going to give us 5. If we put in -5, it's going to give us -6 over -2, which is 3. So we can see that our graph is going to look like that. And then we're going to do the same thing for the other side. So we're going to put in -2. That's going to give us -3 over 1, which is -3. And if we put in -1, that's going to give us -2 over 2, which is -1. And so we can see that this side is going to end up looking like that. And again, our domain in this case is all real numbers except for -3. So we're going to say x cannot equal -3. And the range is all real numbers except for 1. So y cannot equal 1. So that is the domain and the range of this function. All right, so we're going to jump down to the guided practice, the last guided practice question. And I would like you to do question number 5. All right, so we're going to do question number 5. So go ahead and graph that one. You can pause the video until you are finished and then hit play. And here is the graph of guided practice question number 5. Notice in both cases the domain x cannot equal 1/2 and the range is y cannot equal 1/2. The domain comes from setting the denominator equal to 0 and then solving it, so x cannot be equal to 1/2. The range comes from taking the leading coefficients, if they have the same degree, setting them, dividing them, and we get 2/4, which reduces to 1/2. And then you put in a couple of points, and there's your graph. So as we graph these hyperbolas, they're all going to be symmetrical. Okay, remember, if they are in that form, y equals a over x, the domain and the range, the asymptotes, they're all going to be 0. Okay, the vertical asymptote is at x equals 0, the horizontal asymptote is at y equals 0, and you're going to have restrictions of 0. It's going to be all real numbers except for 0 in both of those cases. Then if we look at another polynomial, we can shift them horizontally or vertically. That's going to tell us where our asymptotes go and what the restrictions are on those domains and ranges. And then any general polynomial equation like these last examples, we're going to set the denominator equal to 0 again to find the restrictions on the domain. And then it's the dividing of the lead coefficients will give us the restrictions on your range. So here are the homework sets for section 8.2.